So guys, tell me, on the very first one, would you do the test for divergence? Hell no. On site, you know it's at least conditionally convergent. Because it's a what? Geometric series. So if you look at the, so if it's not divergent, you want to try to show if it's absolutely convergent. Because if it is, you're done. If it's not absolutely convergent, then you have to try to show that the alternating series test shows that it's conditionally convergent. So let me write that down. So you start with, if you can't tell, you definitely start with the test for divergence. You start there. If it's some weird collection of stuff, right? And you need that anyway for later, possibly for the alternating series test. So first thing is limit n goes infinity an if you can't tell. If not obvious. Is that cool? And if this does, if that limit equals 0, then it's possible. I got more work to do. If this limit is not 0, keep going. If it's not 0, done, because it's divergent. I like it. Now, in this first one, I wouldn't even do that. I wouldn't waste my time. It's obvious that's true. It's a geometric series, R is 1/3. Now I just got to differentiate what kind of convergence is it. Is it only conditionally, or is it the absolutely? Right? You've got to figure out what level it is on. So I test for absolute convergence. So in this one, what would that involve looking at? So take the absolute value. And of course, what does that do? As we knew from the very beginning, this is a geometric series. Now be very, very specific. R is 1/3, which is less than 1. So then you don't just say convergent. Absolutely convergent. Now let me ask you this. Do I have to do the alternating series test for this? Hell no, because if that's true, then this has got to converge also, because this is the one that's got an easier job of doing it, because sometimes it's subtracting from itself. Cool. So that's kind of an approach you can take. And very often it kind of depends on how obvious or not obvious the series is I give you. Sometimes that first one is really obvious. You go straight for absolute convergence, because you know it's a geometric series. Right? Just show that and you're done. Number 2, I like that somebody didn't like the cosine. They replaced it like I said you could. Beautiful. I love it. So number 2, where'd you go? There. So if you wanted to, you could put a -1 to the n there, right? So let's just leave it there for now. Actually, it might be a good idea to do that. Might make it easier on you. Because then what's an?
1 over n squared.
And again, that's just like number 1, just a different series. That's a p series where p is greater than 1. So I'm going to go straight for absolute convergence, right? So I'm not going to do these steps because it's obvious. Should be obvious. Let me change that. So the absolute value of an, if I look at this series, convergent, absolutely, because p series, p greater than 1. So if you wrote that as your answer, beautiful. That's all I got to say. You don't have to do integral tests. Dear God. There's no need. We've already done all that stuff. Let's stand on the shoulders of past us, right? All right, so what about the third one? I love it. And again, this is kind of it should be semi-obvious about what this is going to do. No, Jeff. Because what's it trying to be if you take the negative one out of the way? Which is a P series where P is 1. So it would do what? Diverge. So I'm not even going to go to absolute convergence. I mean, there's no need. I know it. But is this, now I got to show it is conditionally convergent. You do have to show that. Beautiful. Alternating series test. Notice I bypassed test for divergence. I'm going to do it anyway because I have to for alternating series. But I already know this thing goes to 0. So first I got to show that it does officially. And again, you might want to always identify for yourself what the actual, no, get out of here, what the actual AN is. Just take the negative 1 part out or the cosine part out. Whatever it is that's alternating, just leave that out. Whatever's left is your AN. Yeah, so this is 0. Check. And then second thing I got to show?
The decreasing.
Decreasing. So yeah, if I do the derivative of this, yeah, so if I rewrite this as 2x to the negative 1 prime, if I wanted to, right? So this would be negative 2x to the negative 2 times chain rule, right? Whatever way you want to do it, doesn't matter. It's not really quotient rule because 1 is not a function of x really. It's just going to go to 0. So I get negative 2 over 2x squared, which you could do stuff too, but who cares? All you want to show is that it's negative, and that is definitely always, no, always negative, which means the function itself is decreasing. Decreasing check, which means what can I say here? Beautiful. It's conditionally convergent. I showed that with the negative 1 in place, the alternating series says it converges. Without it in place, it's a P series that has no chance. P is 1. Conditionally convergent. Yes, sir?
On a test, are you going to ask us to do like a certain type of test, or are we just going to have to like know what test to use?
And that's why 11.7 exists. Because 11.7 is, section 11.7 is everything, all at once. You have to determine when to do what. So just like we did before, we learn all the different possible ways of doing something, and then we have the real thing you got to learn is when do you use which one. So first get really comfortable with each process, and then you would attack 11.7, which is where you have to also figure out when do you do which. Yeah. Let's see. Is that all? There's one left here. And what's number 4 look like it wants to be?
Or 1 over n.
Yeah, so that'll definitely be divergent without the alternating part in there. So I look at that and I just know that's true. From all the work we've done before, n over 3n squared is and 1 over 3n, that's definitely going to be divergent P series. So it's definitely not going to be absolutely convergent. So now I just go straight for applying the alternating series test. I want to see if it's conditionally convergent. So number 4. Okay. So 2 things I got to show. Limit as n goes to infinity of the non-alternating part. That's obviously 0. Check. Secondly, yeah, the derivative of this thing. You guys do that? Take a minute.
squared plus 2 minus n times 6n all over 3n squared plus 2 squared.
Cool. So again, I don't have to worry about the bottom because it's always positive. So I can just focus on the top. So on the top, if I simplify a little bit, I get, yeah, negative 3n squared plus 2.
Minus 6n squared.
Well, 3n squared minus 6n squared is negative 3n squared. And of course, that's immediately less than 0, really.
Yeah.
Right? If you let n be 1, this is negative 3 plus 2 is negative 1. And it's only going to grow more negative after that. So we could do this is it less than 0. N squared would be greater than, because it's going to divide by negative 3. Greater than 2/3. Right? I should have made it x's, but oh, too bad for me. So n greater than square root of 2/3. I'm not going to worry about the negative side of things. So it's decreasing almost immediately for n, because n starts at 1, and that's bigger than square root of 2 over 3. So for our n's, this is always decreasing. So it is not good enough to show me A1, A2, A3, A4 and say, well, there you go, it's decreasing. It's not good enough because it could do this. This is the way you prove it. The quickest way you can prove it. So yeah, overall, what is this series then? What kind of, yes, conditionally.
So say the limit didn't equal 0, then we would just say it's
Divergent, done. Yeah. So you wish for some of those.
Yeah.
I'm not going to give you too many. All right. So mostly that was a definition thing. Absolutely convergent versus conditionally convergent. There wasn't really a lot of new stuff in this. We already talked about alternating series before. Okay. So here's the next thing. Because where would this be really difficult to use? We saw one of these earlier today with the factorial in it and all that kind of stuff. When you start throwing together factorials and exponentials, things get really weird. And I can't even take derivatives. So I couldn't even apply the alternating series test and so forth. So I need to come up with some other way to do this. And the next thing we're going to use is called the ratio test. So I'm going to do your favorite thing. I'm going to derive the ratio test. You're just going to watch. You don't even have to take notes. You never have to do this yourself. I just always want to show you where things come from. And it's kind of cool. Let's see, I don't know if you guys will agree with me, but it is kind of cool. I gotta let myself little notes. All right, let me just let you absorb that for a second. I'm going to prove it to you first, which actually kind of means I have to assume the first part of it is true, which says that if this limit, now what does this here mean? It's a ratio of what?
Like the second term.
Yeah, good. The next term over the term before it, right? So if that limit, so I just take all the divisions of the A3 divided by A2, A4 divided by A3, and forever. If that's approaching some number that's less than 1. Okay, so what would that mean if that was true? That would mean, okay, so for one thing, it certainly seems to be decreasing. So the neat thing that you just pointed out, that I was going to point out later, but this is the perfect time to do it, is that the ratio test kind of uses some things that we know from before. They're kind of inherent in the background of this. So a lot of our earlier tests required decreasing functions. So this actually puts that in here. I like it. So here we go. This is the weirdness. So this is true. Here's the first part of the weirdness. Let's see if you guys get this. If you had a number that was less than 1, could you find a number that was between that and 1? We say it again. So if I have a number that's less than 1, here's my number. Can you always find a number between those two? That's a weird property of real numbers. Yes, you always have to be able to find a number between them. Right? You can just sort of take the average. Right? You will always be able to. So, I'm going to choose. And now, if this is true, if this approaches a limit that's less than 1, then that means at some point, at some big-ass n, some of the other proofs you've seen uses this, at some point it starts doing something specific. At some n, this is true. Oops. I'm going to pick R to be that number that's in between L and 1. No, Jeff, so it's greater than. So I want R to be in between L and 1. All right, stay with me now. So let me slow down here for a second. Exactly what you said earlier, but a little more specific. If this ratio approaches a limit, then that means at some point this ratio has to be less than some number that's in between L and 1. Let me just let you absorb that for a second. So for example, if L is 0.9, and the limit of this ratio is 0.9, at some point in the sequence, it's got to eventually be less than 0.91, for example. It's got to be less than something in between these two. Because it's going to L, right? So at some point, it's got to be less than some R value. Now, why do you think I'm using the letter R? Where do you think this might be going? It's going to be some kind of geometric thing. I like the ratio. It's going to be some kind of geometric. Now watch. So at some point, this ratio of sequence elements has to be less than some R value because it's going towards L. So at some point, it's got to pass R by on its way to L. Maybe. In which case, I can multiply that up. Why am I allowed to multiply that up? Because the absolute value of that is always positive. Otherwise, I'd be careful with the sign tripping, right? But thankfully, that's positive. I can multiply it up. How are we doing so far? And again, this is a proof. If you don't totally understand it, I can't remember if the book does this. Yes. Oh, cool. Oh, good. They basically do it the same way. Good. Holy crap. They do it exactly the same. So, an plus 2 is less than what? Help me out. An plus 1 times R. And what's an plus 1 less than? An times R. So an plus 1 is less than an times R, R squared. So if I keep going, now here's the geometric part, right? What's true about R? What's true about R? It's true. It's less than 1. That's the important part of this, right? I'm trying to construct a geometric sequence. And if my R is less than 1, then this is going to converge. Now, let's see if anybody... Everything I'm talking about right now is only true for some big-ass n that's somewhere between 1 and infinity, right? So what I've done is I took this guy and I broke it up into these two things. Let's say like that. So I'm talking about this guy right now. What's true about this guy here? Is there any way this could be infinite?
No.
Why not?
To a specific number n.
Because I'm adding a finite number of times. There is no way in hell it's going to go to infinity. You can start with 18 trillion billion and add it 18 trillion billion to the billionth power times, and it's still finite. Infinity laughs at that number, right? It's another way to look at it. So everything I'm talking about right now is this one. If I can show this converges, then that plus a finite number is still a convergent situation, right? I know I've already lost about half of you. But still, I'm gonna keep going because I'm crazy like that. So I can keep going with this. I can keep, like, R cubed would be an plus 3 and so forth. So this sum here, since R is less than 1, this part of it, the one that starts at, I made it start at after n, but that's all right. Starts at n plus 1 and goes to infinity. That part has to do what? Because it's geometric with r less than 1, this one must converge. And of course, like I just said earlier, if that's convergent and that's a finite number, then overall this thing is convergent. Cool. In fact, this whole thing, I keep forgetting my absolute values. This is all about absolute values of these things, right? So it's actually what? It's not just convergent, it's absolutely convergent. Beautiful. So that's what the ratio test does. If you pass the ratio test, you are absolutely convergent. If you fail it, you're divergent. And if, so here's the whole thing. You can see it on your little handout. Converges absolutely if L is less than 1, because that relates to R being less than 1. I don't even show you, prove the second part, do I? If R is greater than 1, it's going to diverge. That's part B. Diverges if L is greater than 1. And it kind of makes sense. If the limit is greater than 1, that means it wasn't really decreasing, right? Somewhere it at least stayed the same, if not was increasing. Okay, maybe. And I put a little note there, put a little box, so it's really important. This is good for when you have exponentials and factorials, exactly the things that screw us up possibly in the other tests we have. I don't want to do an integral test with a factorial. I don't know what the hell that is. All right, so let's do this. Let's try one of these out, and then I'll let you guys try out the rest. You guys pick one, 1 through 4. What do you want to do together? 4. 4 looks yummy. Let's try it. Now this is where you really have to start being comfortable with factorials. So if I saw n plus 2 factorial, how could I start to rewrite that? n plus 2, n plus 1. And I can stop anywhere I want to and just put a factorial that says keep going. Right? But I can stop wherever I want to. That's going to happen to us a lot in these kind of things. Because it's going to make a ratio of the next term over the previous term here, right? That's what I want to do with this test. And are there any conditions to be able to use it? There's just one condition. It's kind of hidden. The infinite series of non-zero terms. Right, so it's got to be non-zero. Okay. So certainly that never equals 0, because the top never equals 0. Are you with me? And one quick little thing before I get too far. What is this? It's defined to be 1. Exactly. It's not 0. It's defined to be 1. Okay. All right. So let's see. How do I do this? So what's an plus 1? What's that look like? N plus 1 factorial squared. Let me see how I need a couple of these. There you go, Jeff. Over 2n plus 2 factorial, right? Because you distribute, replace every n with n plus 1 and then simplify. And it's going to be over, and I really don't need absolute values here, really, because this one happens to everything is positive. Is that cool? Okay. Over an. So, and in fact, we're going to make that even better. We're going to start always doing this, multiply by the reciprocal. So I already know what an is, staring me in the face. So the reciprocal of that would be 2n factorial over n factorial squared. All right, now, the whole problem is, how do you simplify this thing, right? Because now I want to do what to this? What am I doing with this ratio? What have I not written down up there yet that I need to do? The limit, good. So I want to find the limit of this ratio. So I just want to build the ratio first. Make sure we all saw where that came from. Now how in the hell do I start simplifying this. This is a good one to pick. It's really kind of evil because we got squares on top of factorials. But what's another way to write this? It's a little better. Anything squared is that thing times itself. Good. It's a little bit better to write it like that because then I can attack both of those.
Factor out the 2 on the bottom and cancel out.
No, you can't. It's a good try. But unfortunately, factorials don't work like it because they're based off of multiplication, not addition. So you can't factor 2 out. You have to factor 2 to the whatever power it would end up being. Good board. All right, let's look over here real quick. The bottom there I could just write as n factorial, same way. It's a good first step to kind of break your stuff up. Now, between these, do you see how this kind of thing becomes useful? I mean, what is n plus 1 factorial if you start to rewrite it? N plus 1 times n, stop, factorial. Don't the n factorials cancel? So this is n plus 1 times n factorial. Now, does everybody see that? I can start writing, what's n plus 1 factorial mean? Multiply all the way down to 1. But I want to stop when it matches with something else. So I can do that for both of these. So then n factorials cancel. Kick ass. So I got rid of all my factorial mess that's really screws us over. I almost said something else. Now what do you think I could do with this? Similar to what we just did. What do you think? What is 2n plus 2? If n was 7, what would this be? If n was 7, this is 16, right? If n is 7, that's 14 plus 2 is 16. So if I rewrote 16 factorial, it'd be 16 times, which is 1 less. So don't make a big deal. Don't freak out about the 2n and all that crap. You just want to make it 1 less than it currently is. So how many times I'm going to have to do that before it matches up with something else in there? How many times will I have to break this out until it matches up with these dudes? Twice, right? Because the first time I do it, so it'll be 2n plus 2 times 2n plus 1 times 2n. And I know I stop there because that matches up with this dude. Ooh, I know you love this. Now, on one level, I think some of you guys, if you get into this, right now, I don't know, you haven't really seen enough to make a decision. But what I always loved about this is a little more concrete. You can really just directly attack the expression. You haven't been able to do this. It's always been, it's a little less than this, and it's my ceiling. It's been very vague. Don't get me wrong. I love that stuff still, even though I had that tone. But this is just so much more concrete. It's just so much, you can see everything happening. That dies. What's the limit as n goes infinity of that over that? You can do it. What is n plus 1 times n plus 1? Sure, but even better. N squared plus 2. Now why am I doing that? Because then I get polynomial ratios and I can just take the ratio of the coefficients of the highest degree terms, right? Boil it down to something I'm used to. The bottom was 2n plus 2 times 2n plus 1. 4n squared plus who cares? I like it. So the limit's 1/4, which is, what's important about 1/4? It's less than 1, which means my series absolutely converges. I like it. Or converges absolutely. You can say it either way. Does it converge? Absolutely. Okay, maybe. So you guys try it, number 1. So first set up that ratio and then take the limit. If you have factorials, you know how to break them out. Sorry about that. Yeah, that's exactly what you need to be able to do on this. And please don't, this whole thing is all about, the first one I didn't do absolute values. Why didn't I do absolute values? Because it was already positive, right? So never carry that into this work here, it just muddies it up. You're always looking at the absolute value. You're always testing for absolute convergence for these ratio tests. So an plus 1 would be times the reciprocal of what this says. Yeah. You can see why. This is a good example of why it's good for factorials. We already knew it was good for factorials because the whole infinite part of it goes away. And it's good for exponentials. And this is the one thing that people seem to have some trouble with before. But when do I add powers? When I was multiplying like bases. So I can rewrite this as what, Jordan? 2 to the 1 times 2 to the n. Kick ass. And this one, of course, I can rewrite as kick ass. So then the n factorial dies. The 2 to the n dies. What's the limit as n goes to infinity of 2 over n plus 1?
0.
0, which is less than 1. Which means absolute convergence. I like it. Now, real quick, if that did not absolutely converge, yeah, I want to make sure nobody does too much work. That would mean that our L came out to be greater than 1, and that means it does diverge. There's no reason to go back and do like an alternating series test. You don't do extra work. Now, if L equals 1, ratio test, you can't use it. You got to use something else. So if it's ever inconclusive, you have to go find something else. Let me see. And look real quick at the bottom of the page. This is very useful because, for example, if I had, let's see, I didn't really put one down here like this. look at number 2 on the very bottom of the page. So, could I do that in any other way that we've looked at so far? I could not. I so desperately could not use ratio test on that. I don't know if you guys see why. Because all the n's would become n plus 1. Right? So you have n of these, and then you have n plus 1 of ln of n plus 1 over n plus 1. I mean, nothing would go anywhere. It wouldn't do anything. It would so desperately suck. So thank God we have a very obvious, this is the most obvious when to use this test. You use this test when you have stuff to the nth power. Right? So you could use it on geometric series, but why would you? Geometric series are easy. I don't need it, but it would still come out the same way. So all this says is if the limit as n goes to infinity, not the ratio, but just the straight up nth root of the absolute value. So it's still testing absolute convergence. And thank God the outcomes are the same, right? If I take that limit and it's less than 1, that means it converges absolutely. You can remember that the L is sort of like R. Why? Because it really is. It's just like R from a geometric. So the results of the test are very easy to memorize, which tells you I'm going to make you memorize them.
So the
right?
root test pretty much just gets rid of the n power.
You gotta love it. So the root test, so this is called the root test. And you can see why we call that take a root. So if I had something utterly disgusting like number 2, that you absolutely cannot do any other way. There's no other test you could do this. Oh, hell, I wouldn't want to do an integral test. It's basically impossible. Screw that, right? And can you imagine trying to take the derivative to show this is decreasing, to use some other... Hello? Yeah, no, thank you. That is remarkably impossible just about. So if I use the root test, the limit as n goes to infinity of the nth root of this just becomes what? And of course that limit is one we should know by now. Oop, what happened? The nth root of this, the n's and the nth root cancels. That's the whole reason this thing exists. The proof is very similar to the other one. If you continuously take roots of something, it's going to approach 1 in a way. So actually, if you do it correctly, the proof says this is going to eventually approach something that you can make less than r. So it's going to be very similar to the other proof. What's this limit? This limit is, I am tired. What do you want from me? The limit is, please. So what's the L'Hopital's? Make it x. So it'll be 1 over x, and that's 1. So of course that limit is 0. We should have known that right here, because ln grows a lot slower than this does. And of course taking derivatives shows that. Derivatives are rates of change. So bam. So what does that mean? No. Yes, because this is less than 1. Good. So this is absolutely convergible. Freakiness. All right, that's plenty. So don't forget, a week from today is our next quiz. 11:4 to 11:7. Herminio, did you come in? Justin Heyer. Sean. Where's Sean at? I saw him. Oh, thank you. Yeah, it's just some homework that matters to get to. Angel. Did you just doing it as I can.
So I'm not going to be here.